and eventually it came out. But in doing this, I sort of realized that in addition to all of these experimental tricks, there was a lot of theoretical questions that were interesting, both kind of fundamental and sort of in methods. And this is sort of where I'm going. I still use this in my own research. So after this, I developed something called a feedback trap, which is a way of taking, if you have a particle, a Brownian particle diffusing in a fluid, there's no potential, but a lot of sort of basic statistical physics ideas can be summarized as you have a particle in some kind of potential, maybe a double well potential, and maybe you want to see the particle hop back and forth or something like that. So there are lots of statistical physics ideas, problems, and so forth that reduce to looking at the motion of a system, some kind of a Brownian particle in a potential, can either be overdamped or underdamped, often overdamped. And so we created a way, and I'll talk about this on Friday, of sort of creating these with a feedback loop so that you could create essentially arbitrary so-called virtual potentials where the dynamics that a particle feels is created by the feedback loop and not by a direct physical mechanism. So we'll see that later on. But then we use this to actually study some problems of fundamental statistical physics. So a double well potential with a very high barrier compared to KT. So if this is the barrier height and it's much bigger than KBT, then if it's a little bit bigger, then you can study things like the Kramers problem. You can wiggle the things and get stochastic resonance. So these are all sort of famous statistical physics problems. But if you have a very large barrier, then it's stuck in one state or the other for a long time. And then it can serve as a 1-bit memory. So it's got 2 states, you're either in the left or the right. And so this turned out to be a nice place, a nice setting to look at what's called the Landauer limit, which is a fundamental limit on the cost of erasing information. And again, I'll get to that a little bit on Friday. So in the meantime, I also was encouraged to try to take this article and expand it somewhat. And so that I think the people who asked me thought it would take me a couple of years, and it took about 10 years. But that's mainly because this happened mostly in sabbatical. So you'd work on it, and then there'd be another 6 years, and then you'd work on it a little more, and so it had a very non-linear progression. But eventually I did, and in doing that, I learned a lot about the topic and realized that there's a lot of parts that are of interest to people in lots of different parts of physics. And so that's kind of what I wanted to introduce in these talks. Okay, so as I've said, the applications can be in technology. Of course, there are lots of things in biology. If any of you are interested in biophysics, controlling gene expression, controlling DNA replication, these are all things that go on within the body. Of course, there's larger scale things like homeostasis. Our body temperature stays the same. Even when the outdoor temperature is going up and down, our body temperature is varying much less. So there's a regulation of temperature there. And blood pressure and so forth. So it pops up all over, and as I've tried to argue in places of fundamental physics. Maybe we can start by sort of listing what would be some of the goals that you might want to do when you control something. So I've mentioned regulation. And so here, you have something that would normally drift around, but you want it to be basically constant. You can also try to track something, and I've kind of mentioned that here. So you have some curve like that, and you want your system to follow it. You can try to make state-to-state transitions. So you might have a system that is in one state, and you want to make it go into another state. And the typical example that I'll talk about just as a simple version of this would be a pendulum. Let's say maybe you have a pendulum that's down, and you'd like to turn it into a pendulum that's up and balanced and maybe stay balanced. And that sounds like a silly toy, but as we'll talk in a little bit, it actually is a sort of a simple situation that represents a lot of interesting ones. You can also use control ideas to create collective effects where there aren't any. So you can the classic example of this would be, for example, synchronization. You have a bunch of oscillators or something, and you want them all to go in phase or with a definite phase relationship. It's one. Stabilization would be another. So I briefly mentioned this, that if you achieve an unstable steady state, then you want to maintain it. So you need control for that. The virtual potentials I mentioned. And then one can go on. So there's just lots and lots of applications. A lot of what I'll talk about sort of relate to these first three, I guess. But yeah. So this is some of the things that you could want to use control to do. And then the question is sort of what are the sort of overall ways of doing this? So there's passive control. And you might think, well, you know, how can you control something without doing something? But if we think, for example, of a potential, let's say we have some potential u of x, then in equilibrium, this would be some Boltzmann distribution, and it would be something like that, say at some temperature. And so you could think of, you know, designing a potential such that you would have the steady state distribution that you want. Okay, so it is possible to control things without sort of doing anything beyond the initial design. But most of control that people talk about are active in contradistinction. So you're altering, I mean, in all of these active ways, you're altering P of x by applying some kind of non-equilibrium forcing. So it could be some steady state forcing and you get a steady state, or it could be time-dependent forcing. But within active, then you can do this without sensors. So in the, you know, so typically sensors are using to measure some property. And if you don't use them, then we would say this is open loop, or sometimes feed forward. I'll explain a little bit this terminology later, and sometimes people will make subtle distinctions between these two, but I won't. So for example, one way of achieving this would be to have something where our potential now has another control parameter, which might be has a control parameter lambda, which might be varied as a function of time. And so it's altering the shape of this potential. And so as you alter lambda, you would have a P of x and lambda, for example, in steady state. So that would be a very simple example of some kind of control, which is not dependent on measurements or sensors. And if you weren't doing that, it would be you could use sensors. And so this is called closed loop for reasons we'll talk about, or feedback. And so here, just to keep with this kind of notation, then our lambda would now become a lambda that is dependent on the state of the system and perhaps on time as well. And so the typical thing is you make some kind of measurement, you have some x, and then as a function of whatever you find out in that measurement, you decide to do something. So these are sort of different options that one would have for implementing control. The kinds of sort of physical systems that carry this out, they're quite varied. So you have things like, I'll call them just gadgets, which are just, that's not an official name. That's just a kind of a shorthand for things like your flush toilet. So it's a mechanical device that is sort of set up so that when it's functioning, it in effect has some kind of feedback control. Remember when you flush on the toilet, the water level goes down. When the water level goes down, there's a ball that sort of goes down with it. That opens up a valve. The valve then fills up the water. And then as the water fills, then the rising ball will close off the valve. This is a modern version, if you will, of something called the steam engine governor, which Watt and Boulton invented in the end of the 18th century. And that was that allowed a much better control of steam engines and was a crucial step in the Industrial Revolution. But I think toilets are a little easier to picture for us, maybe. There are also natural systems that have feedback. So I think people by now we're used to hearing about climate feedbacks. You know, if you have ice in the Arctic that reflects sunlight, that keeps it cool. As it warms up, the ice starts to melt. The water underneath reflects much less sunlight, so it warms up even more. And so that can sort of flip from an ice-covered to a water-covered situation, maybe faster than we would like. That may be coming soon. So getting a little more technological, there are analog control systems. So these would typically be, you have some kind of system, and you have, say, an electronic circuit that effectuates the control, and then its output, usually through some kind of power amplifier to affect the system, and there's an input, usually through some kind of sensor, transducer that converts a voltage, let's say converts a physical property into a voltage, and then that voltage interacts with the circuit. There's a digital version, of course, of this, where in effect this circuit becomes a computer program, and then you have to have something to convert the digital output into a voltage, and then it looks like the analog. And likewise here, you would have a voltage that's converted to a number and then fed into the computer. But otherwise, they're the same. Okay, so this is sort of just I guess the abstract introduction. To start to do something with this, and I should say, I really hope people will stop, ask questions as I go along, and yeah, feel free to raise hands or shout out. So at its basics, you might think of control systems as sort of, just like dynamical systems theory, where you might have some vector x, could be an n-dimensional vector, and obeying some nonlinear differential equation. So if f is some nonlinear function of x, then this can encode a quite wide range of dynamics and lead to chaos, strange attractors, steady states, periodic motion, you name it. But where things in control theory differ is that what people study is not quite this, but slightly different version, where this f will now have a variable u, which will be thought of as an input to the system, and will also specify what you measure of the system. So a control system is sort of the dynamical system, the dynamics, plus an input and an output. The engineers sometimes will call the inputs sensors and the outputs actuators, but inputs and outputs are probably simpler. And so by adding these elements, we'll see that has quite a changes things quite a bit. In this general formulation, both f and h would be nonlinear functions. A great deal of sort of classical traditional control theory is actually done for linear dynamics. And there are a few reasons for it. One is maybe not a great one, which is that linear dynamics are the ones that we can solve things for. But as we'll see, if you set things up correctly, you can sort of decompose a lot of control problems into sort of nonlinear, sort of simple, well, simple, but basic parts and linear around them. So we'll see that it's more than just sort of assuming that neglecting nonlinearities. But we'll start off kind of neglecting nonlinearities. So, for example, you might have a system, and if there's a fixed point, some f such that if we evaluate it, some x naught and some u naught is equal to 0, then if this is 0, then x dot is 0, and so everything is constant. And so we can expand around that and write our x as some x naught plus x1, u is u naught plus u1, and these are constant, and the corrections are functions of time. And so when we do that, then we can do a Taylor expansion. So this will be x1 dot, because this is constant, is equal to f of x naught plus x1, u naught plus u1, which is of x naught, u naught, and that's just 0, plus df dx at x naught times x1 plus df du at u naught times u1, and higher order terms. And similarly, the measurement, so we want to distinguish between the internal state of the system and what you actually measure. And often usually these are different. So even something as simple as a pendulum or harmonic oscillator, you typically would only measure the angle or the position of an oscillator and not directly its velocity. So we'll come back to that, but the measurements are often of either a subset of the quantities or even something that's not exactly what the internal state corresponds to, any internal state component. And so here again, we would have y naught is y1 is h of, and then the same, sorry, h x. These are x naught and u naught. And so then if we sort of clean this up a bit, then we would have a linear system that's of the form. I'm going to drop the subscript 1 here. And so A is df dx evaluated at x naught and u naught. B is df du at x naught and u naught, and so on for C and D. And so these are matrices. If you want to just sort of visualize them, it's something like this. So this would be this is x dot. This is our x dot here, and so this is n, and so this is n here and n here. But these inputs, you might have m inputs. So this is the u. So this is a, and so then this has to be m, and then n in this direction. And then similarly for outputs, we might have p outputs. And so this is the C matrix, so it has to connect to the state. So this is n dimensions and then p dimensions. And the D is has to go from the U, which is so it's M here, and then N here. So if you put all these together, actually, just you can sort of remember their dimensions because they pack into a matrix like this. So this is the dynamics of N by N. This is the number of inputs M in this direction. This is the number of outputs P in this direction. Okay, so that looks a little abstract, but let's just do a simple example. So for a pendulum, that mass M and length L, and this is the angle from the bottom. So if we write things down in scaled units, we can write it as following. Oh, sorry, for the moment, let me just call this a torque. So this is the second derivative of the angle, sine theta, and so the state here, x, for example, could be theta and theta dot. The input is just u equals tau here, and then the output, say, it could be y equals theta. Notice that, I mean, this could be, I mean, you might have a device that measures velocity directly, or gives you something that involves both position and velocity. So there's a lot of choice, but the simplest one would be just to measure the angle. And so then in this language, this would be like x dot is d by dt. So these will now be x1 and x2. And so in this language, it would be x2 and minus sine okay, so x is theta, so this is the first derivative of theta is theta dot, so that's consistent. And then the second derivative, this is theta double dot, is minus sine of theta, sine of x1 plus u. And so this is indeed a function of the state vector components in the input. Okay, so it's just a way of writing these out in a slightly systematic way. And so, but you guys, question or? Okay. So as I mentioned, this pendulum would have two fixed points, so it could hang down or up. The fixed points are theta dot is 0, and theta is either 0 for down or pi for up. And so we can linearize this around either of those fixed points. So for example, when it's in the down position, it would look like okay, so this says that d by dt x1 is x2, and d by dt x2 is minus x1, which is the linearization of sign about x1 equals 0. If we were doing this around pi, then this would be about -1, and so this would flip its sign. Okay. Okay. So at this point, if we had more time, I would sort of take a long detour to point out how once you once you formulate things in this way, particularly in the case where the dynamics are stationary, so they're time invariant dynamics, which would mean that these matrices are just constants. So you're always about the down state or always about the up state, for example. Then a very natural language to address things is in frequency space. For historical reasons, in control theory, this is done by a Laplace transform and not a Fourier transform, but essentially it's the same thing. And so in that kind of view, you would develop things called transfer functions. And the view would be for a transfer function, we have u going in, y coming out. And if you just take everything and just take Fourier or Laplace transforms, if they're Laplace transforms, you can express functions like u of t would go into the S domain. If it was Fourier transform, it would go into the frequency domain. They're related just by S is I omega. So that's why I'm saying they're basically the same thing. So right, like y of S would be y of t negative st, for example. And because it starts at 0, when you start manipulating them, you get initial condition terms, which sometimes are useful. And so that's one reason why they like them. And then in between, there would be what this system is G of S, which in some be defined as the ratio of the output in Laplace space to the input in Laplace space. So this is a very nice and intuitive approach. And one thing that comes out of it very naturally is something called PID control. That's proportional integral derivative. And it's a control algorithm where it looks sort of like the following. So here E is the so-called error. So it's the difference between some reference and the output. So if the reference is a temperature that you want something to be, then Y would be, R might be the temperature of the room that you want, and R might be the temperature of the room you want, and Y is the actual temperature. And you might want to define it the other way, but the historical definition was use this sign. So this says that you would put a correction, and if you want to think of temperature control in this sense, that's proportional to the error. So if you're 1 degree below the temperature you want, you put in 1 control unit. If you were 2 degrees, you put something twice as much, and so forth. And so this is the P part of the algorithm. The I means that you take the integral of the error over the past history. And the reason for doing this is qualitatively that this allows you to come to a steady state that equals the reference without any droop. You see, if you just had this term, what would happen is that if the room temperature were ever the temperature that you exactly wanted, then the error is 0. And so the output is 0. But if the output is 0, then it means that you're going to not be heating and it will go down below room temperature. Probably for here, I should make this an air conditioning and cooling example, but for Canada, it's a heating example. And then the derivative part is a kind of anticipation part. You see that the temperature the error is growing rapidly, so you know that maybe you assume you had a big perturbation, and so then you try to correct it before it has a chance to get away too far. So this is, I mentioned this just because I think 99% of the applications use this algorithm. So I feel like in experiments and industry and I think technological applications. So I would feel remiss if I didn't at least mention this. Okay, but I want to continue really in the time domain. And I should say this was all developed sort of mostly in the US in 1920s to 1950s, maybe 1960 be the cutoff. A lot of the work was done at Bell Labs, the communications company. Some of the people are Nyquist and Henrik Bode, a Swedish-American scientist. And so this is sort of a kind of classical topic of control. But since time is short, I wanted to really focus on a formulation that works in the time domain. And in the time domain, we just stay with this formulation here and keep going with it. So it's a little more abstract in the sense that you'll notice here our X kind of disappeared in here. So it really was just relating inputs and outputs directly to each other. We're adding a kind of internal abstract layer of this system state. And that's why I was making the distinction between the X of the internal state and the observations. Okay, they really are two different things. So, and the X is really something that is in the theorist's imagination. Okay, so apart from being straightforward and just keeping going the way we're doing, we'll see that we can handle noise in a nice way. We can handle multiple inputs and multiple outputs in a nice way. I mean, here I've already sort of set it up for multiple inputs where we've got several M inputs and P outputs. This is most convenient when you only have one input and one output. And you can do nonlinear systems as well within the same sort of overall setup. Okay, so we'll keep going on in the time domain. So maybe I'll erase the frequency domain. Weird. Sorry? I actually get I thought it was almost like we went a turn, but all right, anyway. Okay, so the first thing is to realize that we can explicitly solve the linear equations, right? So we have, where did they go? X, maybe I'll try. Yeah, we have x dot equals ax plus bu, and y equals cx plus du. Usually, actually, there's a tendency to let the d drop because you can always redefine y since this is the input feeding directly to the output. It turns out that if you were to write down an honest model of a system, d has to be 0 if you write a complete physical model of a system, because it means that essentially the input is propagating to the output instantaneously. But there's always, I mean, unless the input and the output are co-located, there's at least the speed of light connecting them two. Often we drop that, but in a physical system, in a complete physical system where we put in all of the physics, we wouldn't have this. But in a practical system, we would often sort of say, this represents all the short time scales where you can instantaneously get the output is affected by the input. So I mean, sorry, maybe this is, so this is something like, when you have something like Ohm's law, that you put a current through the system and then you get a voltage. That voltage, when you turn on the current, that voltage can't appear instantaneously. It always has to take a little bit of time to appear. But often we neglect that. Anyway, I'll often not worry about the d. And in that case, we can just write down the solution. X of t is e to the at. It's called x naught. I'll call it x of 0 plus integral from 0 to t prime. T prime's right. Okay. I think it's when I move too fast or something. Okay, so this is just basically very much like a first order equation, except that we have to remember that A is a matrix. And so it's really, e to the at is the identity matrix plus at plus a squared, b squared over 2 factorial, and so on. Okay, so it's a matrix solution of the simple 1D version. of it. And if we were to put, for example, u is delta of t, then we could evaluate this integral and just get e to the ATB. And this is kind of like this would be the impulse response, also known as a Green's function. So again, something that's familiar, but in a different notation to what we're used to. And so in a first order system, for example, a spike like that would lead to an exponential decay as a response. In a second order system, the response could be underdamped, overdamped, and critically damped. With overdamped with two exponential time scales, e negative lambda 2t. And then this is with a damped exponential. Okay, so this is just like a simple harmonic oscillator from classical mechanics courses. And of course you could have, I mean, this is physically a hard input to apply. So often there's, one could apply a step input and look at the step response and so forth. Okay, so this is sort of the initial setup. And what I wanted to talk mostly about for the rest of the time is what might seem like technical question, but is kind of a basic one when you're starting to think about control, which is just, what is possible to, what can you control, or is it possible to actually control it? Wrapped up, because we talk about both inputs and outputs, there's another question which will be, can we observe a system? In other words, I've already mentioned that what you typically have is a y that has fewer measurements than you have components of the state vector. So you might say, if I just observe some subset of the state vector components, and maybe they have noise and things like that, can I actually know what the internal state of the system is? And sometimes the answer will be yes, and sometimes no. Clearly, if we're observing a harmonic oscillator and you observe the position, then by finite differencing, you can estimate the velocity, right? So in that case, you could say, knowing a couple of, keeping a history of the observations, I can then generate the missing state component. But the question is that always possible? Likewise, I didn't emphasize it, but often the number of components of the input is also less than this. So for example, in the example of the pendulum here, we have one input, the torque, but again, we have two components. And if I want to drive the system to an arbitrary state, can the one input take the two components of the state to an arbitrary place? Okay, so these are called controllability and observability. And I think I'll do it here. And I'll focus on controllability at the beginning. So what I mean by, so the technical name is controllability. And mostly I'll talk about a system with a single input. Well, here we're just talking about the input, so just a single input, but we'll generalize after that. So a controllable solution would be that there's some u of t that takes a system from x naught to some, this would be like x of 0, to some x tau at some time tau, to an arbitrary x tau. So I can start in one state, and then sometime in the future, I want it to be another state. And then we're asking, is there a u that exists that would take the system from here to here? Okay, so it's if you want to picture, be something like this is x naught, this is x tau, and this is x of t, but I want some u of t. I'm not asking to solve for it just yet, but just does it even exist? And so the set of the so given a set of possible controls, then the set that you can reach of xt's that you could reach starting some would be the controllable set. And if you can control everything, it would be a controllable system if the set is essentially the size of the whole state of the system. So it's, I think, rather than starting with the formalism, let me just start with some examples. And then we can see what this means. So x, how about, so just, this is just a one-dimensional state vector. So just this is just a scalar plus u of t. And so you look at this and if you stare at this a moment, you'll realize that it's obvious that this is controllable. Anybody want to try to make an argument? Well, I mean, you could do it the fancy way, but a very simple idea is that if you want, let's just imagine that you wanted to have the system go through some trajectory, some desired trajectory x d of t, then this could be anything the way I'm writing it down. So if I just wrote d, put d's here, then I could just say that solve for u is, if this is differentiable, then this is the u that makes that trajectory. So this is called inverse, sometimes inverse engineering or inverse control. Usually you can't do this, okay? This was helped because we had a one-dimensional state and a one-dimensional control. In rare situations, though, some non-obvious systems actually are invertible in this way. So the most famous example is the quadcopter, the drones with 4 propellers. So they actually you can generate trajectories using something a little bit fancier than this. But sometimes, okay, so there's a whole game in terms of like which systems can you do this. This is actually asking for more than what I was saying, because I was defining controllability as just sort of a statement about the big initial point and the end point, and I didn't say anything about the trajectory. So this is actually a much stronger thing, saying that it can follow the specific trajectory, not only start and end where you want it to be, but in the middle be anywhere you want it to be too. Usually when people ask in controllability, they don't necessarily ask for this much. Let's try another example. So this one dot, Q dot. Okay, so this is x. So this is a particular example. So you see we've got x1 and x2. So would this be controllable or not? Just the way I've written it down. Again, it's a simple situation, but it's mostly the notation that we're trying to get familiar with. No, to find a u. So you want a u of t such that x could be driven from some state that's specified by x1 and x2 at time 0. So this would be like x naught, and it's actually in the plane. So there's 2 coordinates, and this is x at some other time. And is there a u of t that can get me from an arbitrary one to an arbitrary one? Yeah.
U doesn't appear in the second equation.
Yeah, that's right. So the U doesn't talk to x2 at all, so it can't drive it to an arbitrary value of x2. Okay, so this is no. Yeah, and for example, there are other sort of pathological examples like this. So for example, if we take a U and just abstractly it goes into one system and then another system, then the same input is if these are the same systems, it's going into this system and this system, so it can only drive them in a correlated way. Okay, so this would also be no. Okay, so let's try one more that's not quite as obvious, but still simple. So it's if lambda1 and lambda2 are the same, then that's kind of this situation. So let's think about the case where lambda1 and lambda2 are different. But this U is it's just coupling through one, this is 1 and 1, so it's coupling equally into these two systems. Sorry, it's weird. I didn't say and I didn't move. And there's no theory on this one. Yeah, so that's what one might think, but in fact, this one is controllable. Okay, and it's a good exercise to just try to write down. I mean, so the brute force way is just to use the solution that I had and just propagate it from an initial condition to an arbitrary later condition, and then one can see that it's possible. But let me try to I'll try to explain it in a different way. Okay, so before I get into an intuitive thing, so there's a test that goes back to the 1960s and to a guy named Kalman, which is called the controllability tester, and it involves the controllability matrix, which is defined as follows. So the B is this input coupling, well, for one input, it's a coupling vector. A is the dynamical matrix, so A acting on B, A squared acting on B, and all the way to A to the n minus 1 acting on B. So if remember A is n by n dimensional, so this will be an n by n dimensional matrix, and here we're assuming one input and one output. And if the test is to see whether this is invertible. So if the determinant of WC is 0, then it's not, and if it isn't, then it is. So we can go back, for example, to let's say this example here. So we have A is minus lambda 1 minus lambda 2, B is 1 1, AB is going to be minus lambda 1 minus lambda 2, like that. And so then WC is going to be B, and then AB is minus lambda 1 and minus lambda 2. And then the determinant is going to be lambda 1 minus lambda 2. Okay, so by this test, it would say it's okay unless lambda 1 and lambda 2 are the same. That doesn't make it any more intuitive. So why does this test, or what is going on with this? So I guess the main trick is that when we, maybe I shouldn't have. So in this, the main trick is that this definition of e to the at would go out to infinity, okay? However, there's the Hamilton-Cayley or Cayley-Hamilton theorem that says that a matrix satisfies the characteristic equation, its own characteristic equation, right? So then that means for eigenvalues. And so that means that by the time you get to t to the a to the n, you can re-express a to the n as a sum over the lower coefficients. Okay, and so every higher power can be re-expressed in terms of lower power, which means that this can also be written as sum from j equals 0 to n minus 1 of some alpha j, which will involve time, times a to the j. So that instead of this being an infinite series, it's just a finite series. And then the impulse response was just e to the at acting on b. And so if you let this act on b, then we can write this as sum of j and minus 1 alpha j of t a to the j acting on b. And so the statement then that a matrix that's composed of these columns from a to the 0 to a to the n minus 1 is not invertible says that the impulse, if you give the system an impulse, that impulse is sort of projected and felt over the entire space of X. Yeah, so for example, in general, one could write down the value at some time as this matrix B, A squared B, acting on, and here it will just be like 0 to tau. It'll be like alpha 0 tau minus t of t and so forth, and then the same thing for alpha 1 and alpha 2 and so forth. So if this matrix here, this is our controllability matrix, then is acting. So it's either with the impulse input or general input u of t. Then this u of t has projections on the whole space of the x's of the internal state, and so therefore you can find a u that will get you from one point to the other. I don't know if that does that make it more intuitive, or I mean, one still has to maybe play around with the specific example that I said to sort of see that it works. But sorry. Yeah. Oh, sorry. Yeah. So the argument up to here is with a delta function, but this is just sort of generalizing to say that, okay, now if we stick in a u, this will be, we can write down the explicit solution. But again, it's the same idea that this u will again project onto the whole space of x's unless this has a singular structure. Okay, so just a few notes on this. So again, the controllability really just means going from here to here and doesn't say how you go. So we're not in general asking for the trajectory. If we had more inputs, then the test is actually exactly the same, except that now we would just ask that this have full rank. So again, the output space is still spanning the state of X, but now the input is larger because we have more inputs. Another thing is that being able to get to here, you could get to here. It doesn't necessarily mean that there's an input that would hold it. That's again just like the trajectories. We're not specifying that, so that would be another trajectory, and you might or might not be able to do that. Let's see. And the other thing too is that as we saw in our some of these examples that didn't work, like a system like this, you would still control the system in a subspace. And as long as all you're interested is in going into the subspace that is controllable, that might be good enough. Okay, so sometimes asking for arbitrary control might be more than you really care about. The other thing is that everything has been linear so far. And part of the linearity means that however big a U we need, we can take. So in this argument, the tau here is arbitrary. And if you think about it, that sounds totally crazy, right? It means that I can go, here might be this room, there might be the far side of the galaxy, and tau might be a nanosecond or something, right? So clearly, there are systems where this won't be possible, but that's because there doesn't exist. Okay, maybe let's not do the relativistic example, but let's just say in a classical world where we don't have to worry about speed of light limitations, that just if you want to go from here to Cali in 2 minutes or something, in principle it's possible, but not with a car that you have, because there's a maximum acceleration and so forth that you can do. So saying that you have a U that has some maximum is a kind of nonlinearity, okay? So everything I've said is just for linear systems. If it's slightly nonlinear, then often if the linear part is controllable, then a small deviation from nonlinearity wouldn't affect it. There is a less general formalism based on Lie brackets and fancy geometric concepts to test for nonlinear systems controlling. Again, that's something that we don't have time to get into. There's the other thing is that it kind of goes with the, U can't be infinite. That if you go to bigger and bigger systems, then generically this controllability, the ease at which you can control a system, the amount of control effort, the amplitude that's needed, will typically grow exponentially with the size of the system. So that means that even if there's a system that in principle control you, in a big system, you may quickly get into a situation where at least some of it would require inputs that are larger than you can do. And even computing whether this is possible can become hard in a large system, because its eigenvalue, the condition number between the ratio of the largest eigenvalue to the smallest eigenvalue, again, typically grows exponentially in n. So one of the things that happened around, so this classical theory was developed by Kalman in the 1960s, but then around 2010, people were revisiting this in the context of network theory. And in a network, this A matrix, so when we write down, this is a matrix connecting, Aij connects, Xj with Xi. And so you can start to think of the components of A as defining a matrix. So if an element is 0, then that means that if my states now are sort of nodes in space, that a non-zero component of Aij might be that node I is affecting node J, and a 0 component means that they're not connected. So the structure of A can be mapped onto the structure of the network. And so people who were interested in networks got interested, and in controlling networks, got interested in this in around 2010 or so. Barabasi was one of the people. Yang Liu was working with him on this. And so they realized, they and other people realized that even though this in principle, even for linear systems, gave a complete answer, it's not really always necessarily a practical answer. And it gets even worse if you start to think about designing networks. So when I have an n by n network, then given in dynamics A or connectivity A for networks, and given a structure, an input B. So well, in this one here, this is 1, 0. When we did the harmonic oscillator, remember it looked something like, and so U coupled through the velocity term. So here in each of these, we have a structure for B. So this answers the question, given given A and B, is it controllable? But if you had a network and you were trying to design a control, you might say, well, I'm given the A, that's the network that I'm interested in. Can I design a B that will make it controllable? And again, for a small network, this is not so bad if n is not a large number. But when n becomes large, then even to think about all the different combinations, you'd have 2 to the n possibilities of B's that you might have to explore. So even answering like, how do I design something there? And so one of the advances that they made was to then draw on techniques from graph theory and come up with polynomial time algorithms for finding controllable B's that made the system controllable. Yeah, so these are some of the things that I wanted to talk about for controllability. I have just a couple more minutes. Of course, I'm not getting quite as far as I wanted to, but are there questions about this? Because I'll switch gears just slightly at the end. Yep. Okay, so I'm sorry. Well, the determinant it's really full rank. Okay, so determinant in the full rank means the determinant is not 0. So maybe I should have just immediately said full rank. So it's that the input has projections on an n-dimensional space, and so once it does that, then you can solve it. If it is, here we had an example where the space was, let's say, 2-dimensional. If these were one-dimensional systems, then it's a one-dimensional subsystem. This is a 2-dimensional system, but it's only being controlled on a line where they're equal here. And so you want this U to project onto the onto a subspace that's equal to the dimension of the full state. And then, okay, then it's not entirely obvious that should always work, but then you really can actually solve. I mean, in some sense, it means that I think I erased it now, but that relationship between X and U it can be thought of as like a matrix thing that's invertible. And but it doesn't uniquely define a U. I mean, there are many U's that will work because U is a curve, and this is just n-dimensional. So you have a lot of freedom in your U. Okay, I wanted to say a few words about the sort of other problem of observability, and I'll come back to this on Wednesday, I guess, the last day. But I just wanted to point out that we asked, can U lead to an arbitrary manipulation control? The other question that you can ask is on the output. If I observe Y in the past, can I infer the state of the system, the full state of the system right now? And so there's a test for it, and the test that's equivalent to this. Let me just write out the answer, and then we can explain a little bit where it's coming from. Observability in U form. And this one. So you form this matrix here, which is also with one observable. This would also be an n by n matrix, a row vector. This would be a row vector, and then this is another row vector, and so on. And so if this is full rank, then the system is observable. And to start to see where it's coming from, let me go back to that sort of way of sort of writing down the matrices that I showed briefly. So notice that if I took this set of matrices and just took the transpose of everything, then I'd have A transpose, C transpose. Sorry, I'm not trying to draw them to scale, but I'd have another set of matrices. And this is also could be viewed as a dynamical system where now this is the input and this is the output matrix. And in fact, there's a duality that you can establish between dynamics for a linear system going forward in time and adjoint dynamics for sort of the transfer going backwards in time. And the backwards in time comes when you compute the adjoint. There's essentially an integration by parts that introduces a minus sign for like the d by dt term. And so it turns out that a lot of what you can say about controlling a system maps onto a similar statement about observing a system, except that the system you're talking about is this adjoint one. And so you map like the transpose of the output vector becomes the new input vector, and so on. And so from that point of view, if this system is quote unquote controllable, then it means that your original system is observable. Okay, so one can go through and derive it in more or less the way that I did, but this is sort of a short version of it. And since time is short, I think I'll stop with that. And then the last thing that I wanted to mention were just sort of two things, and I have more in the notes, and I'll put the notes online so that people can read a bit more of the story. But the outline of what I would go on next and keep talking about is that if a system is controllable, then I can let me just. Then the claim is that if I'm staying with linear systems, if I introduce a control matrix K, so this is going from the end state to however many inputs you have. So if you have one input, this would just be a row vector, and this would be like the dot product of K and X. So if you introduce a control of this form, then right, so we have X dot is A X plus B U, but U is minus K X, and so this is A minus B K X, and so this is some A prime X. So we would say that, okay, this is a feedback control because it involves the state of the system, and if we apply it, then we get closed loop dynamics A prime. So this is equivalent to another dynamical system with no input at this point. And the claim would be that if A and B are such that the system is controllable, then I can choose K such that this A has arbitrary dynamics. Okay, so I can make this, for example, have eigenvalues of arbitrary thing. And so I'm not sure how strict we are in time. I think I may just leave it as a claim and put the example in the notes, or. Okay, well, let me state and then the second part is that, okay, you would say, okay, that this is great, but we need the X in order to do this. Okay, so, and we don't have the X, we have Y. Okay, we have the observations. But if it's observable, then observable means I can go from a past history of Y to an estimate, let's say, of the state. And then the full claim is that I can design a control where instead of this being the unknown hidden X, this is actually the estimate of the state, and that using the estimate of the state as if it were the true state, then I can control it in an arbitrary way and get arbitrary dynamics. And in a linear system, the problem of designing the control and of setting up a structure to estimate Y, which I think I'm not going to. If I take 5 minutes over time, that's what I would talk about. Okay, okay, then I'll go back and talk about it. But using that structure from Y, you get X hat. Then you can design these separately and end up still with this closed loop control. So the kind of full picture in the time domain is that you have your observations, you use those to estimate the state, and then you use the state estimate as if it were the true state, and then you design it using this method here. And the statement is, even without sort of thinking about methods, it's just saying there's enough freedom and everything covers all the right spaces that you can just take the components of K and then make this have arbitrary eigenvalues. Okay, and so again, it takes a little bit more time to prove that, but that's the content of it. Yeah, let me just show you the structure. So the structure that people use in order to estimate the state is a little unusual, so it's worth writing down. Let me just, so we had, this is our original dynamics, and let's say y is equal to cx. So then the trick that people use in control theory, which I feel probably has more applications in physics than we realize, is to set up what's called an observer system. So the observer is a copy of your physical system that's going to run, say, in a computer. So you might say, well, I can just, what about setting up a system like this? Okay, so this sort of looks okay, but let's look at the difference. So if let's set E is x minus x hat. So this is the difference between the true state and what you're estimating. So if we just subtract this, we get E dot is equal to A, E, and then these cancel because you feed the same, and you know your inputs. And so you can feed them into both your model and to the physical system. Okay, so these cancel out. And so we have A. So if A is a stable system, then this looks like it might work in the sense that the E of t would converge to 0 in the long time limit if A had only negative eigenvalues, so that everything was exponentially decaying. But you could first of all see that if A happens to be unstable, then this doesn't work because this would blow up. But for good control, it turns out even this is not good enough, because intuitively you want to be able to observe the system and act on it more quickly than the system changes. Here, your estimator will be changing at the same time scales as your system itself. So you really want something that's faster than the system. And the way to do that is to add in a feedback term here. So I'll introduce an L, which is the difference between the actual observations and what you would predict. So we could say that the prediction would just be this. So this is, and so if you're, if these two systems are synchronized, then the predictions would match then the observations would match your predictions. And so this would just be 0, and you'd have E equals 0 propagating. But now you can show then that this L alters the rate at which this converges, because we'll have A, E, I guess it'll be minus L x hat. And this is Cx, and so this is C E, and I think I'm okay. I'm not quite sure about this. And so this will be E dot is A minus L C E when the dust settles and the signs are correct. And so now again, if it's observable, you can choose this to have arbitrary eigenvalues. So that's kind of the end of where I wanted to get today. I haven't said very much about how would I actually go about picking, say, the L components of L or the components of K to do this in a nice way. We'll come back to that, I guess, tomorrow. And there are different ways of doing it. Heuristically, you might think that, oh, I want a system that would converge, have a control that makes this dynamics infinitely fast, that the observations would converge infinitely fast. And so that turns out, that sounds too good to be true. And the reason it is that if you ask for a K that makes this dynamics converge infinitely fast, the values of U that you'll need will be huge and probably larger than you can do. If you ask for an L that makes your system synchronize, so this observer system basically synchronizes with X. And so if you ask for it to synchronize too quickly, then when you put in noise terms, which we won't do until Wednesday, then the noise terms, when you put a large gain on the noise, will kind of amplify the noise. So the noise will sort of set a cutoff to how big we want to make this term to be. And so we'll see that on Wednesday. But this is sort of the basic structure of how you can sort of take at least a linear system and systematically design a control that goes from the observations to this abstract internal state, and then from this internal state to the control. As I said, the historical way was to do this all in frequency space where you don't have this. But here it'll turn out that these kinds of arguments will be things that we can start to generalize when we have nonlinear dynamics, and also when we have time-dependent coefficients here, time-dependent dynamics here. So again, there are reasons for going the extra route in abstraction. Okay, so I think that's all I have for today, but I hope there are some questions.
So you were mentioning that usually people don't ask for full control in the sense of trajectories, but isn't in some sense asking for full control on the final points the same thing as asking for full control on the trajectories? Because you can always just go from one point inside the trajectory you want, then you go to the other one, and so on?
No, so sometimes, for example, the control that you might want to do can be very weird. Like, you start from here and you want to go to here.
Mm-hmm.
Sometimes the control that we would calculate might be end up, looking like that. So it can take some very non-obvious ways to get there, and then this wouldn't be possible at all.
Okay, thank you.
Imagine like I had some cliff in there or something like that. Like your Montserrat or something. We can see it here, but you really have to get to it by going around the big.
Thank you, Professor, for your lecture. I have this question. There is some restriction with the state that I can connect. For example, in the pendulum example that you give, there is a stable point where theta is equal to 0, and there is an unstable point where theta is pi. So it's possible to control the system to get from one point to another in a finite time?
Yes, but that's now you're asking a question of the nonlinear system. And so in that case, it is, but it's a little more complicated than what I was talking about. So this would just be for trajectories that are either around the bottom one or around the top. But yes, we'll talk about how to get from bottom to top tomorrow, I guess.
Okay, because I think there is an infinite amount of time to connect that both states.
No. So here we're talking about finite time connections typically.
Okay. Thank you.
In your case, couldn't one just argue about counting degrees of freedom? I mean, U has a certain amount of degrees of freedom, and the internal degrees of freedom, and that you cannot control 2 degrees of freedom with one single variable, for instance, one single variable. And if you have a very many high dimensional space of internal degrees of freedom, it's very difficult to control them with one single U. So I mean, just
no, but U has in effect an infinite number of degrees of freedom because it's a curve. So we specified it every time.
Yeah, but you want to achieve a specific value.
Yeah.
At the end.
So you're taking an n-dimensional system from one n-dimensional state to another n-dimensional state, but the U has in some sense infinite dimensional.
Mm-hmm.
So whether it's controllable or not, it's not just a question of counting directly the dimensions of the U.
Mm-hmm.
There is this controllability theorem, but it doesn't tell us how to choose U, no? That's
tomorrow.
That's tomorrow, okay. Looking forward to see.
At least partially tomorrow, yeah.
So this is the linear theory so far, no?
Yes.
But at the end, when things go non-linear, is that possible to control chaos, for instance, a chaotic system?
Yeah. So I mean, there isn't a general theory of there isn't a general nonlinear version of this. There's some special cases that you can answer. So there's cases where it's like a linear system plus very small nonlinearities. There's a case where the f of x and u is some f of x plus, I don't know, g of x u. So there's some special cases where you can make some statements, but as a general thing, no. At least, not well. I'm pretty sure no. I mean, but I mean that doesn't necessarily mean it's impossible. But
I'm not sure if I understood correctly controllability. Is it in some sense similar to the concept of ergodicity of a system?
well, not exactly. I mean, here, I mean, ergodicity, would say that if you just let a system evolve without any inputs, is it like visiting all parts of space in proportion to the measure? And here we're asking really about, I'm in one part of this state space. Okay, you could say that's like phase space. And I want to have an input to the system that's going to bring it to a chosen different point. So it's asking a slightly different question. But I mean, they both involve sort of trying, in some sense, trying to get to all parts of spaces. But here it's with a deliberate intervention as opposed to just the natural dynamics of the system.
Okay, thank you.
Staying here in the linear regime, how will this look like if you open the system? If there is a bad, for instance.
I'm sorry, if you open the system?
Yeah, if you couple the system to a thermal bath, for instance.
Oh, okay. So that you can think of as sort of like another input to the system, right? So the thermal bath will be producing stochastic perturbations to the system. So in the, so in one way you could say that, well, that's, we can just enlarge B to have another input, which would be the noise input. But often people would sort of write it out as kind of a special case because we can't control the thermal noise from the bath is not something that we can control. So then it would just be like an extra input to the system, but that doesn't affect its controllability, right?
But
You might say, how well can you control if you want to like fight these things and regulate it to be constant, then you could say, given an input of thermal noise, with what precision can I design some kind of control to say stay near some point?
But could the noise be used to do feedback here?
Well, if you could control the noise, yes. But I mean, in some sense, the noise usually is what we can't, we call it noise when we can't control it. I mean, the noise, particularly when you get to nonlinear dynamics, how to say, or even in linear cases, the fact that you have noise will impact how you design the system. And so again, I think we'll talk about this a bit more on Tuesday and Wednesday. It certainly designs. We'll see explicitly on Wednesday how, as I mentioned, the way you estimate the state, which also then influences how you can control it. It's influenced both by thermal noise that's affecting the system and any direct measurement noise. So in fact, you have two noise sources. And given those two noise sources, you're trying to develop or trying to get the best possible estimator of this X hat that I was writing down. You want this to be, in some senses, as close to the true X as you can make it. And so we'll see how to do that. And so that certainly takes into account the strength of the thermal noise and whether it's white or not and things like that. Yeah. Okay, well, thank you. And I'll try to get some notes posted so that you guys can read in some of the missing parts.
So thank you, Professor Bechhoefer. And let's go to the coffee break.
Question. I have the feeling that this is only true for systems that have unstable points, or it's possible.
No. It's yeah. Sorry. It's
Yeah,
you go through so many
I ask
too
this
fast,
because
but